Okay. So last time we stopped at synchronization, and that's where we're going to continue now. Synchronization is a really kind of a big problem for any processing environment. It's addressed in many areas of computing systems, such as operating system, and in the processor level as well. So when you look at, for example, let's say you have a dual-core environment, which is, you have CPU 1 and then you have another CPU 2. And then if they have a shared memory space, which they share the addresses and they bring the data they need to, and then they compute and write back whatever they have to do, they do. For example, let's say there's an X value, which initially has a value of 5, okay? And then each processor is trying to load this data and then perform some computation and update the data back in the memory. So if you consider, let's say CPU 1 is loading this X from memory into its one of the variables, let's say T0, and then performing an add 1 to this value, x plus 1, so it increments it by 1, and then stores this value into, back to the same address that it just brought from. And then same thing, this is for CPU. Let's say we're performing the same task for CPU 2, and then it's also loading into its register T0, and then you have similarly, increment X by 1, and you store this value, back to the value that you brought from. So let's write it this way. T0 plus 1, and then this will make it clear. T0 plus 1. So when you implement these two, the first processor, let's say, brought the data loaded to T0. Now the T0 will have a value of 5, and then it's going to increment by 1, right? And at the same time, assume that before this is stored by the first processor, what if the second processor also accessed the same data from the same location, and now this T0 is also having the same value as 5, and then since this updated to 6, this will also make it 6. This will store back this value that it just made into 6. It will store this back into here. Now the value of this X will become 6, and right after that, followed by that, this second processor will also perform T0 plus 1, which will make it 6, and then it's going to store this result back into the memory again. So X is going to be 6 again. However, normally what you intended to do was actually not this one, but rather perform this task, for example, followed by this one, or vice versa. So the result that you would expect normally from this kind of computation is normally what? 7. What is the problem? What's the problem? The updates are not done atomic, right? What we mean by atomic is that once this is loaded by this processor, it should have performed its execution and store it. Then the second processor should be able to access it. So this is called the synchronization problem, or atomic execution. And this is really famous in also database area. For example, if let's say you have a bank account which is kept in a database, right? If two clients access the same thing, and then they for example transfer the money, you have to have a locking mechanism to prevent multiple things occurring at the same time, right? Let's say you have an account which has 100 TL in it, and then you would like to withdraw some money from one client. At the same time, you withdraw from another client, try to withdraw the same money. So you withdraw 100 TL from this client and then 100 TL from the other one. You cannot allow this, right? So you have to have a mechanism, locking mechanism, to do that. So this is done by commits in database, which ensures that you have atomic execution. So this is atomic execution. This is the keyword. So you would like to start executing and then finish it, and this is one atomic execution. So to do this in processor, so we would like to not have this situation in our processing environment. As a result, we will try to, synchronize our processors to prevent that. So there are some, measures to do this. In MIPS, we have a certain instruction sequence that we try to prevent such data races. Data races is the name that happens here. So you have a data race because of this access sequence. And to prevent that, as I said earlier, you perform an atomic exchange and finish your execution in one processor and then start executing on the other one. That's atomic. So to implement that, in MIPS you have load linked and then store conditional. So what this does is actually it loads this data to T1 that's stored in this memory location and then stores into the same place conditionally this T0 into this memory location conditionally. If, however, there's another load after, or there's another update before this load, it's going to give you an error. Okay? How does it give the error? It modifies this T0 to be equal to 0. So if some other instruction tried to access the same memory location while you're computing this, it is going to return with this conditional, this store conditional will return a 0 in T0, which will mean that there was a problem between these two instructions. Okay? So the idea is you use load link and you bring this data into your T0, perform your execution, and you try to store this conditionally into this area again. However, if there was an update onto this memory location, the processor will warn you with giving a 0 value, returning a 0 value back into this register that you just used. So you can use this value, compare this T0 with 0. If it is 0, you can say that, hey, there was an error between these two instructions. If it wasn't 0, you can say that execution was correct, so I can continue with my, processing. So let's give an example of this. For example, here, you try to add, you first try to exchange the value of a certain address space, which is given with S1. And what you do is first you add S4 to 0 and T0, which actually moves the value of S4 into T0. So as you can see, T0 is now equal to S4. And then you load this address, the value that is stored in this memory location, into T1. And then you try to store conditionally this T0, which you just computed from S4. Now it has the value of S4 into this. Try to store this memory location. If, however, if this T0 returned to be equal to 0, then you'll say that, hey, there was a problem with my store conditional, which means I need to try again. So which, in this case, if T0 is equal to 0, it will branch back into the try statement. And then we'll try to redo it again until it performs the computation correctly. So what this enables us to do is, it enables you to make sure that between the load and the store, there's nothing happening in the memory. However, obviously you can insert additional instructions in between these two lines. Let's say you have arithmetic operations which doesn't deal with memory at all, will not harm, right? You can just do whatever you want in terms of R-type instructions because you do not deal with the memory with R-type instructions. For example, add, multiplication, whatever you prefer. And if nothing happens, this will run correctly and you will have a value in T0 other than 0, which will skip this and then will swap the value of S4 to T1. So now if you remember, we just copied the value from S4 to T0, moved it into memory, and now we have the value that's just loaded from T1 and we can copy it into S4. So what this does actually is, so you have a value that is stored in register S4 and then you have a memory location. So you swap the values that are stored in the memory with S4. So you copy this S4 first into T0, right? Now T0 becomes S4. And then you copy the value of the data that is stored here into T1, T1 becomes the memory location. And now you copy this back into the memory address. And the last thing that you do is you copy the value of T1 into S4. Right? So this is the sequence. So in order not to break the consistency, you always check whether this is whether there's something else happening in the memory that is trying to access this location. Any question? So this ensures, if there's any consistency issue, this ensures that you have, you don't have any synchronization problem. Okay, now we go into the compilation issues, which is, kind of towards the last part of the chapter. So given a C program, or for that matter, doesn't matter if you have a Java or Pascal or Fortran programs, the program that is written in high-level languages compiled into assembly code. Can you imagine yourself writing code in assembly all the time for all the methods or all the problems that you face today? It's really hard, right? Even writing one simple loop takes, at least you have to pay attention and try to not create any errors. You have to be careful. So in 1975 or so, they used to write every application using the assembly code, using adds and multiplies all the time. The reason is because you have a limited memory space back then. So they didn't have much space for the code. So they couldn't write, they couldn't let the compiler generate a sequence of lines which may span a huge memory space. So let's say at the time they were dealing with not even kilobytes, they were dealing with bytes. So they were trying to fit everything into that small area, and assembly programming was really important because they could just do the exact operation they need to. And also the compiler infrastructure was not really that strong, so they had to, as the years passed, the compilers now are really powerful. They can generate almost even better than a good assembly programmer can write. So compilers convert the code in a really good sense. And now once you write your C or Java program, you compile it, you have the assembly code. Now the assembler comes into play, which converts your assembly code into object code or the machine executable code. And then you most of the time have library routines, right? For example, in Java you have import Java packages that are available within the language lang package or utility package util. You use those packages in order to use those tools that are already optimized and designed for this purpose. You just take them and implement within your code, right? So the linker actually combines the object code that you just compiled for your part of the code, along with the library routines which have already been, generated. So you don't need to every time generate the object code for the library routines. They are already available. You can just pick them and link with the linker. Okay. So what if we do not do this, however, instead include the library routines in our code? What would happen? Instead of doing this, what if I wanted to include my library routines along with my code and assemble it and then continue to generate my object code? What would be the problem? Does the library routine change? Do you change the library routines? No, right? You always use the same library routines which have already been designed and optimized. You just pick them and use them. So the idea is every time when you perform this compilation step, if you embed more and more library routines and files into your code, it would take a lot longer to compile, first of all, and then it will make your code bigger. So to prevent that, what you do is you combine these objects, library routines that are already available along with your object code at the linker step. So this linker actually combines these object codes of your application with the library routines and then generates a machine code or the executable that is available for the environment that you're targeting. Okay. Once you have the executable, the loader actually loads this into the memory. So it reserves a certain memory area and then loads your application and starts your application from the initial line of execution. So this is how C code translation hierarchy would work. Any question? Have you heard the pseudo instructions so far? Pseudo instructions are used for, in MIPS for example, or in any language, are used for representing things in an easier format. Although, for example, as in this given example, you have move T1, T0. What obviously the name suggests is that you copy the value of T1 into T0 is what it does. Okay. However, in the underlying architecture, there's no instruction. In the machine, you don't have this instruction at all. What assembler does is that this is called a pseudo instruction. Assembler converts this into a different instruction which it can represent in the machine with the machine language. So which is in this case add T0, 0, T1. Obviously this is the same exact thing, right? You add 0 to T1 and store it into T0. So that's exactly what we are trying to do here, right?
Why it is not add immediate T1 to T0?
You could do that as well, but 0 is already a defined hardwired register, which makes things faster. That's why they have defined this. 0 is a common value that is used in computation. So they have defined a 0 register, which is part of the register number 0, and that's available just for this purpose actually. Using it more often, it is faster to access. That's why. You could obviously write add immediate with 0. That's an option. But whenever assembler converts this into this pseudo instruction to a machine instruction, that's what it will use for implementing. And again, if you remember branch less than, right? Normally, what do we have in branches? Branch equal and branch not equal. Since the less than comparison is expensive, we do not perform it along with the branch. That's why we have this instruction divided. This is a pseudo instruction again, and is divided into two instructions. When your assembler sees this instruction, it converts it into these subsequent instructions. And obviously, this AT is the purpose why we have the temporary for assembler, AT, assembler temporary. And it sets AT if T1 is less than T0. Otherwise, it is going to be equal to 0. If it is not equal to 0, it will jump to L. So that's exactly doing the same thing. Again, this is an example of a pseudo instruction. Okay. So for example, can you think of another example?
B greater than.
Yeah, BGE, branch greater than. BGT, sorry. Or BGE, or any other version of this branch. Or for example, subtract, which is actually subtract a negative number, for example. That doesn't exist. So let's say you have sub T0, T1, let's say sub I, minus. So what you're trying to do is you would like to subtract 5 from T1 and store it into T0. So what this actually is converted is into add immediate T0, right? T1, and then obviously minus 5. So these are also the instructions. You can use them while you're writing your application. However, know that not all of these are actually machine instructions. They are actually converted to some other instruction in certain cases. Any question? So if you want to produce an object module, as we talked 2 slides previously, so you have to follow these steps. The first one is you have the header, which describes the content of the object module. So you have an object, the header identifies the contents of it, the text segment, the instructions that you have that's going to be executed by the machine, and then the static data segment this is the data allocated for the life of the program. So for example, in Java or C, you have static data, right? You can define some of the variables as static. Those are executed, or those are kept throughout the life of the application. So in those cases, you will store that kind of data in the static data portion. And then relocation info, this is for the contents that depend on the loaded program's location. So you need to pay attention to relocation info. If it is moved to somewhere else, that's going to be updated. And then the symbol table, which defines the references, such as, for example, let's say we said branch equal S0, T0, L1. This is a label which will be kept in symbol table. Okay, so symbol table will keep this and will tell you what is the address of this symbol actually. As we said, we use the offset to represent this, right? So to understand the address of it, you have to look into the symbol table, and the object code will tell you the correct address. And then the debug info, if you have, for example, whenever you run your application and at some point it gives an error, right? It causes an exception, for example. In those cases, this debug info tells you which line of the code actually it refers to. For example, in object code, you have a certain line that is causing the problem, and it corresponds to a certain portion of the code in the actual source code. So this debug info will give you that information to associate any line in the object code onto the actual source code. So when you link, as we said earlier, we said that we have the linker, right? Which actually takes your object code with the library and combines and links them into a single package to run on the machine. So what it does is actually it produces an executable by doing the following. First, it merges the segments. So you have multiple object codes that you're merging into. So you could have multiple .o files in Java or C, for example. The object files are given .o, the name it ends with .o. So this will merge these objects into one object, and then if there are some label issues, it will resolve those. As I said earlier, let's say you have in one of the object codes, you have this label L1, it is going to need to refer to the correct address of this L1, wherever it points to. So in order to do that, you have to resolve the labels. That's also done by the linker. And then you patch the location dependent and external references. If there are certain references that need to be updated by this linking step, you have to do that as well. And these are all jobs of the linker to combine all these objects and the library modules. So that's mostly about this slide. So whenever, as we said earlier, once you have the linker generated executable, you load this into the memory by the loader. So this goes into loader, and this loads it into memory. To achieve this, loader needs to perform a couple of tasks. First of all, it will read the image from the disk and then identify the size of each segment on the memory and create a virtual address space if that's necessary to do so, and then copy the text and initialize data into the memory. So once you have, let's say, arguments in your program that are passed as arguments, right? In any application, you may have arguments that are passed by the user, for example. You will set up those arguments on the stack as we did with any method, right? And then initialize these registers, stack pointer, frame pointer, and then the global pointer. And it will jump to the startup routine, wherever the start of the method or the application that you have, it will go into that startup routine, which is, for example, in Java, where do you go for starting up your application? Where does the application start from? Main, right? So in Java, you go to the main and start from there. That's what the loader does, and jumps to that address to start execution. And whenever it returns, it will do a system call to return back to the environment where you called the application. Okay. So this is a logical step. If you follow, read the header, identify the segment size, allocate enough space, and then copy the data and the code into memory, and set up arguments on the stack, adjust the pointers, and start execution. So that's pretty much what you would expect from the loader. Now we said that this linking happens in the offline process, so which is a static linking. So in this case, you generate your executable at an offline stage. So when you do this, the linker generates it, generates the executable at an offline step, which means you have all these libraries included in your object as before the linker step, right? So this is called static. Static always refers to something that is not done online, which means offline, which is, for example, is compilation is a static operation or a dynamic operation? It's a static operation, right? Because you perform not at runtime, it's at compile time, so it's a static thing, which means it doesn't change throughout the running of the application. So this linking that we just mentioned is a static linking. Instead of this, what they came up with is a dynamic linking. Dynamic linking means that you link the libraries as you use them. You do not link all the libraries beforehand, assuming that they're going to be needed. So what's the advantage of dynamic linking as opposed to static linking? Yes, one advantage is that you would have a lot less space for your executable. Once you need the library, you will have the dynamic links to point to that library directly, instead of trying to link them, link the whole set of library at the beginning. So that's one of the advantages, and also it saves from execution latencies as well, as we will see shortly. And when you look into the advantages here as well, it requires procedure code to be relocatable, so you can relocate the library that you have and then dynamically load that library instead of another one, which will give flexibility. And then avoids image bloat caused by static linking of all referenced libraries. This is what your friend just said. If you include all those library references, then it's going to create a huge image which will be bigger than what you could normally need. And automatically picks up new library versions. Let's say there's the string library which just came up, and they just implemented a better option for string manipulation, for example, as a library. If you, instead of the previous older one, if you include that one, that would be better. So you wouldn't need to use the old and not so good version of the string operations. Okay, so dynamically you can pick up the new library routines that are just developed for the same application. Any question? Okay, now this is just showing an instance of dynamic linked library. So DLL indicates dynamic linked library. That means, instead of static linking, you perform a dynamic link. So the first time, actually, what happens is that the left part indicates first call to DLL routine. So let's say you are calling, if you look into here, it has a jump and link, and then loads and jump and return. So it returns back to wherever it is, and when you jump register to that address. And whenever you look into this thing, you see that it refers to an address, an indirect address, and you go into the memory to this location of the address, you fetch the data from there, and it's actually pointing to the dynamic linker loader routine. So if you happen to access this dynamically loaded library, what you do is the first time you have to go through all these steps and then access the DLL routine from a lot of memory indirections, as shown here, with many memory indirections. However, once you locate the DLL routine's place, the next time the subsequent calls, the next call after the DLL routine will be a lot easier. Now you would know the address that your library is actually connected, the DLL routine. You can immediately go in there and then fetch the DLL routine, access it easily. So the first time accesses for DLL routines are, taking longer time, as opposed to the later accesses will be a lot faster. So the first time is a pain, but the next ones will create no problems as static accesses. So this has a little bit overhead, but it's worth, as in many compilers or linkers currently use this kind of strategy for both C and Java. Okay. The details are, if you want to read in further detail, you can check the book and also other sources. So Java applications behave a little differently. What's the difference in Java? Yes, you have Java virtual machine in Java, which actually means that whenever you compile and assemble your application, what you do is you compile it for the Java virtual machine. So for the JVM. Okay? You're not actually compiling for the architecture that you have underlying. So for example, if you have an Spark architecture, Sun Spark architecture, you still can use the same Java code, right? If you have a Java application .class file, what you do, you can immediately run it on Sun Spark. And then you have another architecture, let's say MIPS, you can run it. Or x86, you can run it, Intel architecture, for example. How come this happens? Because they have different instruction sets. So what we do is we compile all these classes to the Java virtual machine, which you should already have, installed in these architectures. So what happens is that when you compile it to JVM, the Java virtual machine will convert them into the actual machine code. So JVM versions will definitely differ from one architecture to the other one, right? So when you go and try to download the JVM for your processor, you see that you have different versions for each architecture. So the Java program will be compiled and you get the Java bytecodes, which are native language for JVM or the Java virtual machine. And now you use this Java virtual machine and then the Java bytecode that you have to generate the compiled Java method. Okay. So this Java virtual machine is the one actually, converts whatever you have as a bytecode into the machine language. And the JVM instruction set is really simple, which uses the Java library routines along with your bytecodes. And it's, most of the time converts one instruction from JVM into the corresponding instruction in the underlying, instruction set. For example, in let's say MIPS, you have a certain add. You have a JVM version of the add, which is converted to MIPS version, and then in another Spark, this add is converted to the Spark version of the add. So not one-to-one compatible, but you have mostly single instructions represented by single instructions in either one of these architectures. So that's the idea. And just-in-time compiler. What does just-in-time compiler mean? Dynamic compiling, yeah. Just-in-time means you compile while you are running at the same time. So the idea is behind this. The idea behind the just-in-time compilation is that you would like to compile bytecodes of hot methods into native code for host machine. So once you compile the first time, actually what you do is you collect statistics about the Java collects, or the JVM collects statistics about the application. So let's say it has a certain portion of the code which takes most of the time, let's say a certain method, which takes most of the time to execute. In that case, what it does is that instead of converting these and running from JVM, what it does is it converts the instructions that are given in this part of the method into the native code instead of the JVM. So it converts the JVM or Java bytecodes into the native code and then embeds it into the same executable. So over and over, as you run the same application over and over, it gets faster and faster because it now knows where to concentrate on and modify it and run it using the machine code or machine instructions you have. Okay? So that's what just-in-time compilation and just-in-time compilers mean. Okay, so this is an example of converting a bubble sort function into the MIPS version of the code. So you have seen other examples how you would convert a given C code into a MIPS version. So this is going to be the same. So let's say you have a swap method which basically swaps the, let's say you have a method, let's say you have an array V. So if this is array V, what this does is actually, there is the kth entry which is given with the second parameter here, int k, and then it takes the kth entry into temp and then just swaps with the next element. So it's just doing this. Performs the swap between these two elements in the array. Okay? And assuming that V is in A0, K is in A1, V is in A0, and then K is in A1, and you have temp that is stored in T0. So these are already given and they tell you to compile this into MIPS. So how would we do that? Obviously what you would do is you need to first go into the memory that is the address location of this kth entry, right? To implement this swap method, which is the first argument. A0 is the argument, remember, right? A0 means the argument. The first argument indicates that the address of V. What does this address indicate? Which entry of V? The first one, right? So it indicates, this points to the first entry, which is V0. So if you wanted to access VK, then you would obviously add 4K to that value. So this obviously does a multiplication by 4, shift left logical, right? If you shift by 2, you multiply by 4. And you multiply this A1 with 4, which is actually the K, right? So you multiply K with 4, so you get 4K. And then add this to the A0, the first argument, which is the V, so that you get to the, you add the base address, you get to this memory location. Right? Once you get to the memory location, now you can load this address, go into this address and load the data into T0. Okay? Once you have the data in T0, you need to swap with the next element, which can be obtained by how? How does it obtain? The next element? Yeah, by adding 4, right? With the offset. So this is the kth entry, if this is kth. And if you add 4 to the address, you'll get the next element, which is k plus 1. And that's what it is doing. And you have T0 have the kth entry and T2 have the next one. And it's just swapping the values. And it stores this into 0 and stores the other one into 4. So it's just swapping the places to store. Right? Any question? And whenever it's done, obviously, it is going to return wherever this was called. So if you have, how do you call a method in MIPS? What do you use? So if I wanted to call swap, what do I use in my, let's say this is my main function and I'm calling swap here. How would I call it? Jump and link, right? So I would say jump and link, and then I will jump into swap. So it's going to jump into wherever this swap is. And whenever I say jump register array, it's going to return back to my return address, which is the next instruction, right? Whatever this is. Let's say if it is add, the array actually points to this instruction. And whenever I say return back to the return address, it's going to return back to this instruction and execute from that point. Okay? That's what jump and link. It jumps to here and stores the value return address as this next instruction. Any question about this? Okay. Now we will make things a little, harder. This is the sort procedure, the bubble sort, and it actually takes again V array and then an int n, and every time it actually sorts the array based on the elements of the array, and it calls, if you look into here, swap vj. So it swaps the elements of the array v, the jth entry, with the j plus 1. So that's what it does. And if you look into this example, again, v is passed as parameter, as an argument, a0, and then you have n in a1. So we have v in a0, and then you have n in a1, and you have I in s0, and then j in s1, right? So let's say we have, I'm not going to write the first part, but let's write this part, because for I0, and then you have I less than n, I plus 1. And you have for j I minus 1, j greater than or equal, and you have vj greater than vj plus 1, right? And then j minus 1. And then you perform a swap vj. This is really complicated here. Okay, now the reason I put here is because I won't have to be able to see it as this. So when you look into this compiled code, you will see that this is the case for the same exact example. So what you do is, let's start from the beginning. Okay, so we have move a0 s2. Again, move is a pseudo instruction, so it's implemented using add instruction. And then you have a0 moved into s2. So what is a0? That's the address for base address for array v. And then you have a1 moved into s3. S3 is a1 is n, so you now have the value n in s3, and you store s0 to be 0. You initialize it basically. And then this is the for first. So this is the first for that you have. And it's checking set less than S0, S3. Whether S0 is less than S3, set T0. Right? It is actually performing this. If your I is, what was I? I was 0, right? This is I actually initialized, and then it's checking S3. If it is less than S3, otherwise it's going to what? Stop, right? Because BEQ will be equal to 0, T0 will be equal to 0, and it is going to branch into exit 1, which is given not here but on the next slide. Okay. And this is the condition, again, this is the condition for checking whether you have reached the boundaries of the for loop. And then every time you decrement your S0 by 1, you assign j equals I minus 1 in this case, and then start the second loop. So in this case here we have for j equals I minus 1. So this is where the second loop actually starts. And then this is the second test for the inner loop, which is checking whether S1 is less than 0. So this is checking for this one. S1 is less than 0. Where's that one? This one. How does it check? If it is less than, it sets, and it compares with 0. So it jumps into exit 2, which is here. Okay, so this part is checking for the boundaries of the loop. And then again, it checks for the values, multiplies by 4, and goes to the specific memory location in the memory for array v, and compares these two by checking whether if T4 is less than T3 or not, and then jumps into the exit 2, which is here again. So this is one of the conditions it is checking, and then the other condition is this one. Okay, so these two lines is checking the first condition. Okay, it may not be clear, but if you follow it, it should be more clear. This is the first condition, which is this one. This is the second condition, which is this one. So it's checking whether Vj is greater than Vj plus 1. If it is the case, it will continue. Otherwise, it will go into exit 2, so that this inner loop is finished. However, if it is not the case, then it's going to copy these two values, S1 and S2, into A0 and A1, and call swap, jump and link swap. How does swap know its parameters? How does it know the parameters that it's going to use? So I call jump and link swap. Which parameters is it going to use? A1, yeah. We already know that we are going to pass these arguments into A0 and A1, and such that whenever they're passed, swap will be able to use those. So that's why we have these two, move A0 and A1, so that we pass the arguments. Whenever this called, it can execute correctly. And then when swap method we just wrote finishes, it will return back to here and execute from this point on, which will decrement our S1, which was equal to what? S1 was what? Is it J or? Yeah, J. So S1 will be decremented by 1, right? And then, so that it is this thing that you're executing, you decrement J by 1, and then you will at the end jump for 2 tests. So you will go back to the top of the loop, execute it one more iteration, which is going to do it over again. And at the end, once you're done with the for 2 test, which is the inner loop, you'll go out of this and then jump into exit 2, which is this, so that you will increment S0 by 1. What was S0? It is I, so the outermost loop. So you perform this. As you can see, 3 things. First, you initialize the loop, whatever you need to initialize. Then you check for the condition. Then once the loop is finished, you'll perform this increment and then continue executing. And just for the last slide, this is going to be the... Exactly, this is a good point. You need to save the stack, the pointers and the arguments that you used. For example, S registers, right? You have to save before. So what do we do actually is, it was the next slide, before calling the sort method, you reserve 5 register space, 5 word addresses, and then store your return address and all these S registers that you just used. So you store them in the stack, you perform the procedure body that appeared in the previous slide, and then whenever you're done, as I said, exit 1, whenever you're done, you're going to load these values back into their original values, S0 towards S3 and RA, and then at the end you'll adjust your stack pointer to leave the space that you used before. And this will return to the caller which called this sort method. Okay? If you go over this in the book, I would really recommend you to go over it tonight if you have time. It should be more clear if you see how it works for for yourself and study in the book. Okay, this is for today. See you next time. I don't know whenever.